This is another isomer matching example, but it's a little bit different format from the one in my first video. In this one, you're asked to match each of the 4 molecules below to its relationship with the molecule shown in the box. And you'll use each relationship only once, so again we can use process of elimination to our advantage. We have only 3 questions in our process this time because there's only 4 possible relationships, so I deleted the question that helps you to determine whether or not the molecules are conformers. So let's start with question number 1, same molecular formula. The structures here are skeletal or what's called line bond structures. We need to know where the hydrogens are. It may help you to put each carbon in and then determine how many hydrogens are attached. Remember that if we have 1 bond shown, there are 3 hydrogens. If we have 3 bonds shown, there is 1 hydrogen. And again, over here, we have 3 hydrogens. If we count all our hydrogens, we get 8. And there's 1 oxygen. If we do the same thing down here, we have 1, 2, 3, 4 carbons again. There are 3 hydrogens on the end, then 1 and 1 and 3 again. So we have 8 again. So molecule number 1 is related in some way to the molecule in the box. If I look at molecule number 2, I have 4 carbons again. If I draw in my hydrogens, I have 3 on the end. I have 2 right here because there's only 2 bonds to start with. Another 2 there, and another 3 on the end. If I count them all up, I get 10. And there's 1 oxygen. Molecule number 2 is an alkane with an oxygen in it. If you didn't want to count the hydrogens, you could have used the formula CnH2n plus 2. The oxygen doesn't affect the number of hydrogens at all, so we could say 4 times 2 is 8 plus 2 equals 10. If you have 1 double bond, the number of hydrogens is exactly double the number of carbons. So here we have 1 double bond, an oxygen that doesn't affect our hydrogen count. So if we just count the carbons, 1, 2, 3, 4, we can assume there are 8 hydrogens. You can count for yourself to double check me, but this method is very reliable as long as you know that in this case oxygen doesn't affect the hydrogen count. In molecule number 4 again we have 4 carbons. We have a double bond. Even though it's to oxygen, we can still say there are twice as many hydrogens and there's still 1 oxygen. So we've just confirmed that all the molecules except for number 2 are isomers to the molecule in the box. So we found our not related molecule. I'm going to erase the hydrogens on my original structure just so that we can see it better when we're comparing it to the others and asking our further questions. So our next question, we're done with same molecular formula, is same connectivity. So the connectivity of our original structure, we have a carbon with 3 hydrogens on it, a carbon double bonded to another carbon, each of those has 1 hydrogen on it. We have an oxygen, and then we have another CH3 at the end. If we look at choice number 1, we have 3 carbons in a row where these 2 are double bonded, so the second and third one are double bonded. Then we have an oxygen and another CH3. So number 1 has the same connectivity. We're looking for something that doesn't because we are now trying to find our structural isomers. If we look at number 3, it's shaped a little bit differently, but we still have a CH3, a carbon-carbon double bond with a hydrogen on each, an oxygen, and then another CH3. If we look at choice 4, however, we have a CH3 and then a carbon-carbon single bond. So that connectivity is different. And we can also see that the double bond is now between the carbon and the oxygen, when in the original structure we have a carbon-carbon double bond. So the connectivity here is completely different. These are our structural isomers, which is also known as constitutional isomers. So we have found 2 out of our 4 relationships. And we're down to either identical or stereoisomers. So the next question asks, are the molecules superimposable? Is there some way we can take one of the molecules that we're comparing and either pancake flip it, rotate the entire molecule to figure out if it will be exactly the same as the other one? If you look at number 1, you may have already guessed this. If we take the entire molecule and flip it upside down, it will be exactly the same as the original molecule. So all I did for number 1 was turn the molecule upside down. So this one is identical. Hopefully, looking at number 3, you can see that it's not identical as the original. Just to be thorough, we want to make sure that it's not. And you can see for the original structure, we have sort of this zigzag shape here where the methyl is down and to the left. And here we have sort of a U-shaped where the methyl is coming up. So because we've confirmed that number 1 is identical, number 3 must be stereoisomers. So it is a stereoisomer to our original molecule. And if you look at the double bond, we have a hydrogen here and a hydrogen there. I know where my hydrogens go because the angle around the double bond is always 120 degrees. The shape around these carbons is trigonal planar. So now that I've drawn my hydrogens in, hopefully it's obvious that this molecule is trans with respect to the double bond. If I put my hydrogens in molecule number 3, hopefully now it's obvious that this molecule is cis. And cis-trans isomers are a type of stereoisomer.